All right, let's take a look at calculating the gravitational potential energy of an object. The gravitational potential energy is defined as the energy stored in the gravitational field between an object and the Earth, and is stored in that field because that object is some height above the Earth. And so the idea is that gravity likes to pull things down, right? It wants everything at the surface of the Earth. And so the farther you are away from the Earth, essentially the more gravity can act on you, essentially. And so this potential energy, you can think about it like some resistance to gravity. And the farther you are away from the Earth, the more potential stores in that gravitational field. The formula for quantifying the gravitational potential energy of an object is equal to this. M, the mass of the object, multiplied by g, the gravitational field strength, which on Earth is always 9.8 meters per second squared, multiplied by y, the height of that object, relative to some arbitrarily defined 0 point. And this is an important point that I want to make right now. There is no absolute amount of gravitational potential energy. It's all relative to some point that you've defined as the ground. For example, Irvine happens to be about 56 feet above sea level, but you could also be on Mount Everest, which happens to be about 29,000 feet above sea level. And so wherever you are, the ground that you walk on is not exactly an absolute height above anything. And so gravitational potential energy is a relative idea, and it's measured relative to some arbitrarily defined reference plane of 0 height. And you get to define wherever you want 0 to be when you're solving a problem, which is actually really nice. So if we consider like this airplane flying above ground level, we can call the surface of the Earth that it's flying on 0, but we could also, call some height above the ground 0 and measure the energy the airplane would have relative to that point if we wanted to. Now, I'd like to point out here that the gravitational potential energy of an object depends on 2 variables. The first one would be m, its mass, and the second would be y, its height above whatever, again, you've defined as the ground or your reference point. So g is a constant on Earth, and so it doesn't affect our proportionality here. So if you double the mass, right, double the mass, you will get double the amount of gravitational potential energy. If you double the height above the Earth, you will double the amount of gravitational potential energy, right? They will both go up by the same amount. I'll put the 2 there, okay? The U is a term that means potential energy, and so you'll see this U come up again when we get to elastic or spring potential energy. All right, let's take a look at an example of calculating the gravitational potential energy of an object. Now, a great example of gravitational potential energy is a ride that I've been on, and maybe you have too. Supreme Scream is a turbo drop ride at Knott's Berry Farm and happens to be the tallest freestanding structure in Orange County. On this ride, riders are released from a height of 252 feet above the ground and free fall until they reach a height of about 60 feet. If the cart with all of the people in it has a combined mass of 388 kilograms, let's calculate the potential energy of the cart and the people at the top of the ride, and then calculate the change in potential energy from the top of the ride to the ending height of 60 feet above the ground. In order to calculate the potential energy, we will bring up our potential energy equation, which again we will derive in a later video. That will be the mass times g, which is 9.8, times y, the height above the ground. So in this case, our ground level has already been given to us. We're told the heights above that relative ground level. And so we can just plug in our values here. The gravitational potential energy would be 388 kilograms multiplied by 9.8 meters per second squared. And then for our height, notice we've been given a height in feet, 252 feet, but I know I need to use meters in order to calculate energy in terms of joules. So I'll go ahead and do a quick conversion here. I know that in order to get feet into meters, the conversion is 1 meter up here is equal to 3.28 feet. And so I know that 252 feet is actually going to be 66.3 meters. If you plug in this height value into the equation for y, you will get a potential energy of 252 252,000 joules roughly. I'm just rounding here. And that's also equivalent to 2.5 times 10 to the power of 5 joules, if you want to write that in scientific notation instead. All right, now we'll do a very similar thing to calculate the change in potential energy. We can calculate the final potential energy and then subtract the initial potential energy from that. So as a reminder, delta, or a change in any quantity, is just the final of that quantity minus the initial of that quantity. So I can actually plug in the expressions, right? mg, the final y position, minus mg, the initial y position, would be the change in the potential energy. And since m and g don't change, I can actually just say that's equal to mg, right? I'll factor out m and g, yf minus yi. In other words, that's mg delta y. So what I've just done is shown you that the change in the gravitational potential energy is just the mass of the object, the acceleration due to gravity, or the gravitational field strength, and then the y displacement. So in this case, I went from 252 feet, that would be our y initial, which we will convert to meters in a second here, and that was our starting height, and our ending height here was 60 feet, which is our y final. So the first thing I'll do is convert both of those to meters, and then I can do y final minus y initial to get my delta y. So 252 feet in meters is equal to 66.3. We got that in part A. And then 60 feet in terms of meters, using the same conversion factor, is 18.3 meters. So my y final is 18.3 meters above the ground. My y initial was 66.3 meters above the ground. And that means that my delta y here, in this case, is actually going to be negative 48 meters. So now that I have my change in height, or the change in my y position, I can go ahead and plug that into my change in potential energy equation. So delta UG, which is gravitational potential, is equal to the mass, 388 kilograms, multiplied by G, 9.8 meters per second squared, multiplied by that negative 48 meters. And that's all equal to about negative 183,000 joules. And so in this case, the negative sign associated with the change in potential energy tells us that I have less potential energy at the bottom of the ride than I did at the beginning. So the negative sign here does not indicate a direction. Remember, this is still a scalar quantity. It just tells me that my potential energy has decreased from the beginning of the ride. So this concludes our series of videos about kinetic and potential energy. Thank you for watching.